Welcome back. Non-singular matrices. An n by n matrix is called non-singular or invertible if there exists an n by n matrix B such that AB equals BA equals the multiplicative identity IN. So notice, to begin with, you want your matrix A to be a square matrix and you want the B to be of the same size, square matrix. A times B equals B times A equals identity matrix. Such a matrix B is called an inverse of A, and it is usually denoted by B equals A to the power -1. That represents inverse of A. If no such B exists, then A is called singular or non-invertible matrix. Okay? So notice, unlike real numbers, you are not guaranteed in existence of inverse. You may not find an inverse. Okay? In that case, A is simply called singular or non-invertible. Let's look at an example A. A equals 2, 3, 3, 1, 2 by 2 matrix. Let us see whether A is singular or non-singular. Suppose B equals ABCD. So notice this is a 2 by 2 matrix. So if at all you need a B, it has to be also a 2 by 2, ABCD. Suppose B be such that A times B is the identity matrix, 2 by 2 identity matrix. That is, A times matrix B has to be 2 by 2 identity matrix. So I'm multiplying these two matrices. 2 times A plus 3 times C, that's the 1, 1 entry. 2 times B plus 3 times D, that's the 1, 2 entry. 3 times A plus 1 times C, that is the 2, 1 entry. 3 times B plus 1 times D, that's the 2, 2 entry. So this matrix must be equal to 1, 0, 0, 1. So that gets us 4 equations. Notice, how do we get the 4 equations? 2A plus 3C is 1, 2B plus 3D is 0, 3A plus C is 0, 3B plus D is 1. Okay, so you get 4 equations in these 4 variables. So notice, B and D and A and C, they separate out as 2 different batches of equations. So from equation 2, I obtain C is negative 3A. I plug in that C in equation 1. 2A plus 3 times negative 3A is 1. That tells me 2A minus 9A is 1. So 2A minus 9A is negative 7A is 1. A is negative 1/7. So we found A. Now that we found A, we can find C. C is negative 3 times A, so it's positive 3, 7. So we have found A and C using equations 1 and 2. Likewise, let's worry about the second batch of equations. Equation 4 results in D equals 1 minus 3B. D equals 1 minus 3B. Once I have that, I'm going to plug it in here. 2B plus 3D is 0, but D is 1 minus 3B. What does this tell us? 2B plus 3 minus 9B is 0. 2B minus 9B is negative 7B. So 3 minus 7B is 0. Move the 3 over. Negative 7B is negative 3. B is 3 over 7. Once you have B, you can substitute here, find D. D is 1 minus 3 times 3 over 7. So that's 9 over 7. 1 minus 9 over 7. That's negative 2 over 7. Okay, check your fractions well. So now we are able to find B, that is the inverse of A. We found all the four um, variables A, B, C, D. So B, that's A, that's B, that's C, that's D. Okay, we found B, which is the inverse of A. That means A is non-singular or invertible. Okay, example of a singular matrix. Look at A, 3, 6, 1, 2. It is not 0. None of them is 0. Can I find an inverse of it? Well, same procedure. Let's try and find an B, A, B, C, D, such that 3, 1, 6 to this matrix A times B is the identity matrix. Well, this gives us equations. Well, first let's multiply it out. Row 1, column 1, 3A plus 1C. That's the 1, 1 entry. Row 1, column 2, 3B plus 1D, 1, 2 entry. Row 2, column 1, 6A plus 2C, 2, 1 entry. Row 2, column 2, 6B plus 2D, that's the 2, 2 entry. This matrix has to be equal to 1, 0, 0, 1. So that gets us 4 equations. Okay, let's write down the equations. Here they are. Let's do the same thing we did in our previous example. Use the first 2 equations to solve for A and C. Second 2 equations, third and fourth equations to solve for B and A. From equation 1, we obtained C equals 1 minus 3A. Substitute it in equation 2. 6A minus 2 times C equals 0. 6A plus 2 minus 6A is 0. Oh, 6A's cancel. You have 2 equals 0. This is simply not a true statement. 2 equals 0 is a false statement. This is a contradiction. We cannot solve for A. If we cannot solve for A, we cannot solve for C either. Which means, likewise, actually we could stop here, but let's try and find B and D. Use equation 3. Identify D. D is negative 3B. D is negative 3B. Plug in 4. D is negative 3B. 6B plus 2 times negative 3B is 1. That is 6B minus 6B is 1. 0 equals 1. This is also a contradiction. Again, we cannot find B and D. We are unable to solve for B or D either. The matrix B does not exist. Okay, so let me go to the previous page. This matrix is singular, or it is not invertible. You cannot find its inverse. Okay, I hope these 2 examples were useful. Now, if A and B are both non-singular n by n matrices, non-singular means you can find the inverse of A, you can find the inverse of B, then the product is also non-singular. What about the inverse of the product? Notice how the order got changed. AB inverse is B inverse A inverse. Here is a beautiful short proof. Let A, by the way, this is an important theorem. You should be able to prove it. Okay, it's a short theorem. You should be able to prove it. I might ask you to prove this theorem in the exam. Let A and B be 2 non-singular n by n matrices. What does that mean? Non-singular means A inverse exists, B inverse exists, and they are both n by n matrices, such that A times A inverse is I and B times B inverse is also I. Notice the I, or the identity matrix, is n by n, or simply written n. Now, you see, the claim is the inverse of AB is B inverse A inverse, so why don't we multiply it out? AB in parenthesis times B inverse A inverse. Well, we know multiplication is associative. That means I can move the parentheses around. So I'll move the parentheses around B inverse, keep A and A inverse outside. BB inverse is identity. Again, I'm using associative property, move the parenthesis around A and IN. A times IN is A times A inverse is IN. So you see what happened. AB times B inverse A inverse upon all these calculations is simply identity matrix. So AB times B inverse A inverse is IN. Similarly, you may check B inverse A inverse times AB is IN. Again, notice all that it takes is moving the parentheses around. Place the parentheses around A inverse and A. That will give you identity. Identity times B will give you B. Eventually, B inverse B will give you identity again. So, AB is non-singular and its inverse is B inverse A inverse. It's a very short and important proof. All it took was moving about the parenthesis. Make sure you write it down at least once or twice to understand its salience. Okay. Corollary. Corollary means a result that follows a major theorem. So in the previous theorem we saw two matrices being multiplied and two non-singular matrices being multiplied, and we find its inverse, the product's inverse. Now suppose you have more than two, say R number of non-singular matrices A1, A2, A3 to AR. They are all of the same size n by n. They are non-singular matrices. Then the product is also non-singular. Product is non-singular, and the inverse of the product, notice the order got changed. AR inverse first, AR minus 1 inverse next, AR minus 2 inverse after that, and the last one is A1 inverse. So order gets changed when you find the inverse. Well, how do we do this? Well, all you do is write A1 through AR in one parenthesis, multiply by its proposed inverse, that is the AR inverse, AR minus 1 inverse together. Now because we are associative, we can move the parentheses around. All I have done is moved these parentheses here and this here and got the middle two terms together. These give you identity. These two give you identity. Identity times anything is anything. So this times this is this. So we have just forgotten the identity. Again, what do? Take the AR minus 1 and merge it with the AR from here. So pull out the AR minus 1 here and AR minus 1 inverse over here. So the end ones from the middle are to be combined. Everybody else is outside. So the middle one is back to identity. Keep doing this until you get the last one, A1 and A1 inverse. That's an identity. Similarly, what if I placed all the inverses on the left and then followed by the matrices without inverses here? Remember the order. AR inverse, AR minus 1 inverse, that, and followed by A1 through AR. So notice these two have to match. A1 inverse, A1. That fetches you an identity. Then A2 and A2 inverse will fetch you an identity. So it starts collapsing from the center to give you an identity. That's how we prove our corollary. Okay. Let's continue in the next video.